Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Eli Datema. Eli started as a thermal EOIR engineer with Thermal Analytics in May of 2021, and he creates thermal models for military and commercial contracts using Titherm, MuSES, and Cotherm. These models are frequently used to generate synthetic EOIR imagery to train AI and machine learning algorithms. And other technical efforts of Eli involve field test validations, software training facilitation and support, and software development support. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and this presentation. And with that, Eli, if you're ready, you may begin.
Awesome, thank you, Chris. Thank you for the introduction. Like you said, my name is Eli. I'm an engineer here at Thermal Analytics. It's a pleasure to talk to you all today, and today we'll be talking about our maritime capabilities within our software MuSES. We'll just go ahead and get started. So a quick agenda, we're going to talk a little bit about the motivation behind why we want to do maritime targets, do a quick overview of our software MuSES, go about what makes a maritime target different than a ground or an air target, talk about some of the different sea rendering settings, talk about how you can include things like a wake and a plume, and then go over some examples as well as final conclusions. And that should take about 20 to 30 minutes, and then after that we can get into answering any questions that you have. So a quick motivation, introducing the relevant concepts for the proper maritime model attribution and creation, and after those concepts have been applied, we can create that accurate thermal result to help with any vehicle design if that's what you're interested in, as well as an accurate generation of infrared imagery, primarily for the purpose of target recognition, and especially in the last few years that the synthetic image generation is desired for the training processes of AI ML as for target recognition as well. So here we can go over what is MuSES. So MuSES is our thermal solver and EOIR rendering tool. It takes in inputs such as 3D CAD geometry description, part material thicknesses, thermal properties, component heat sources, as well as boundary conditions, such as the sun location, the sky and background for radiation exchange, and air temperature, and at which speed for convective heat transfer to properly set up the analysis environment. Once these are combined, we get a physical temperature prediction of the target, and then we can create sensor images based off of that, which can be specular or diffuse, as well as spectral or across a broad band. And we can also get contrast metrics such as the delta TRSS values and contrast radiance. Being able to gather all this information from our one software is what helps make our MuSES such a powerful tool for those who care about the IR spectrum. And now we can go into what makes maritime modeling different. So MuSES allows maritime vehicles to be modeled at sea. On top of properly modeling the convection between the target and the water, we can model different states of sea and how that affects the waves. When the IR images are created, reflections of the moon and sun will also be seen off of the water surface. And throughout our history, we have developed an extensive library of maritime models, as seen here. Includes anything from simple ships to cargo ships to sailboats, destroyers, and many other types of maritime vehicles that we've worked with. So let's go a little bit more into the actual model creation process. So when you set up the environment, a water background is available. After selecting the water background type, a number of settings can be changed. So the first thing, the water type, includes three different options. The constant, empirical, and first principle models are the three that we offer. The constant water type is the simplest. This sets the surface temperature to whatever core temperature you set as the user. The empirical model predicts the temperature as a function of latitude with adjustments for seasonal variations. The first principle model takes a user-specific depth and creates a one-dimensional model simulating the natural convection and solid conduction through the water layer depths. The surface temperature will also vary depending on solar load and air temperature. A clear, turbid, or a manually inputted other option for surface attenuation can be selected. Solar absorptivity can be modeled or directly set if you have measured data. A core temperature can also be inputted. A correct core temperature will be important for both the proper convection between the ship and the sea, as well as final radiance values of the sea within the renderings. And finally, selecting the paint code option will allow you to change the sea state, which will change paint parameters based off of the environmental wind speed. And you can see a little bit at the end here, according to each sea state, it'll actually show a wind speed that correlates with that sea state. So after setting up the background, proper convection settings can be set up for the underwater parts. Using the H&T fluid setting, a connection between the underwater part and the modeled water will be made. The H coefficient can be set as a simple value, which will maintain that value throughout the whole simulation, or a script can also be linked to the model, allowing any values to change based off of the current modeling scenario. The default water background will be a fluid option in the fluid temperature dropdown due to the background that we just created in the previous slide. So once the thermal results have been calculated, we can go into the sea rendering settings. Going to the sea settings in the signature tab pulls up the BRDF sea parameters. By default, the none option is selected. This will render the ship with no created sea geometry. The background radiance values will be based off of the environmental setup we showed earlier. Selecting the unstructured sea allows the sea to be rendered by creating its own sea geometry. So in the uniform model, a single value is used for the water radiance. The color you see in the renderings will be the total emitted radiance plus the radiance reflected from a directional sky. The three variable water models used in directional sky model, they use the directional sky model ModTran to calculate the sky radiance reflected by the sea. Users can also specify either the Robertson algorithm or cubic spline option for the sky dome interpolation algorithm. The cubic spline parameters can be set to reduce the number of zeniths and azimuths computed for the algorithm. So this will set the number of points around the sky dome where ModTran is called, and radiance values computed for inputs to cubic spline spatial interpolation algorithm. The user can also further reduce computation time by checking the Vary Sky by Zenith Only box. This option can be selected for rendering of night scenarios, which would accelerate the interpolation routine by using a 360-degree average value for all azimuths. But this value must be used with caution for daytime scenarios when a solar position would cause the sky radiance to vary significantly as a function of azimuth. Here you can see the differences between the unstructured sea models. The uniform model with a constant sea radiance shows a slight change in color the further the sensor is from the water. This is only due to the atmospheric interference between the sensor and the sea. In the variable depression model, the directional water model is run once for each horizontal slice in the image. This does give more accurate sea reflections, but does not account for any horizontal changes in the render. The variable azimuth model runs the same as the variable depression model, except does the calculations for vertical slices instead of horizontal. And finally, the variable sensor model computes an individual radiance value for every pixel in the image. This is obviously the most accurate model as it takes into account both horizontal and vertical changes. However, it does take the most computational power to complete. So here's a validation we've done in the past of the unstructured sea model. The sky is calculated using ModTran, interpolated with cubic spline selected. The sea is an interpolated distribution calculated in horizontal slices. So each horizontal slice is a calculated average value of what would be seen in real life. So that average includes both the dark black and the white caps that you would see in the left picture and combines that into one value for each pixel. And the graph on the right shows radiance values as the elevation changes in the image, showing matching results between the measured and predicted data. Now, while this data does match, if you want a more realistic looking picture that better matches the variance in waves and clutter found in that measured image on the left, the next C option might be the option for you. So selecting this structured C option will create geometry on the waterline in order to more accurately model waves and wakes. The created waves depend on both wind speed and direction. As you can see in the image here, water geometry has been created around the ship, and the image shows a pretty clear difference between the created wave geometry and the smooth water geometry outside of that. Yeah, and that the smooth geometry seen outside of that is how the unstructured C option would look. So to properly create this structured C, we first need to input the wind effect. 3 options, the environment, wind speed, and sea state code are given to input this wind effect. The environment option pulls the wind speed and direction directly from the weather file used in the thermal simulation. Wind speed, selecting the wind speed option will allow you to override the weather file wind speed with any speed that you choose. And the sea state code is a drop-down list from 0 to 9 using the Beaufort scale, which has the suggested wind speed listed next to the options. And finally, the override wind direction option will also allow you to override the weather file wind direction data. So here are some examples of the structured C type options. The entire C surface structured type covers the largest area of C with coarse elements. And while it does cover a large area, the elements are large and not very realistic looking. If the render is taken at a very low depression angle, you may also see areas where the C structure does not reach, as it does not cover the sea surface that is very far away from the target, which may show up in the image. The structured only around ship type generates geometry at 2 ship lengths around the ship. As you can see in the picture, the waves are more realistic looking, but unless the picture is taken very close to the target and at the right angle, it won't show in a very large percentage of the image. The user-defined type offers the most customization of the 3. The settings below that you can see below the red box there show the different options that can be set up, such as element size and C disk diameter. This will create the most accurate looking images from most angles, as long as the user sets it up accordingly in the first place. So while separating the underwater parts created proper convection between the sea and the ship, the rendered water line will still have to be set. If the option is not selected, the water line will be set at the lowest Z height geometry point in the model, which may not be the most accurate of what you're looking for. Luckily, the mouse pointer on the right will allow you to select a point on the geometry to make defining this water line position much easier. So you can see the picture on the left is the water line maybe lower than what you would desire, and you would want to move it up slightly higher, showing it on the right. When setting up a C model, a geometry preview is available to make sure it is set up correctly before you start rendering. Maybe you aren't sure what C state or user-defined C geometry is needed, so you just want a quick look. And this geometry preview allows you to quickly visualize these changes before spending the computational time needed for the actual rendering process. Here are some examples of the different spectrum types when rendered. The Pearson-Moskowitz is an empirical relationship that defines energy distribution with frequency within the open ocean. It's a simple description that assumes equilibrium if a steady wind is present for a long time. The John Swap, or the Joint North Sea Wave project, is essentially a fetch limited version of Pearson-Moskowitz, but it's not fully developed. It is based on measurement data from seaways near coastlines in the North Sea off of the Danish coast. The Newman uses a wide spectrum for open seas based on wind speed with single empirical parameter. It's a historic model that has been more recently supplanted by multi-parameter spectra. And the Brettschneider is an average width spectrum developed for the North Atlantic and assumes infinite depth with no swell and unlimited fetch. It's a 2-parameter description based on model frequency and significant wave height. This is more useful for modeling wind-driven seas rather than swell. Another adjustable option is the spreading angle. This is the angle at which gravity waves spread out from the wind direction. 60 is our default, but options 90 and 120 degrees can be selected if that more accurately simulates your environment. So let's go into how we model wakes a little bit. Moving maritime models must include a wake to accurately evaluate their signature. The size and detectability of the wake makes them important in the overall signature of the model. Using the structured C setting, we can actually incorporate a wake within the created C geometry. We can also import a third-party wake. These are pre-computed wakes from CFD or different hydrodynamic particle codes. An example ship file is shown to the right with different options. The X is the Cartesian coordinate along the ship in meters. Y would be the coordinate perpendicular to X, but lying in the plane of the sea surface. Z is the height of the wake. W is the percent of foam within the wake, and that's a value from 0 to 100. And T would be the wake turbulent suppressor, which would be a Cox-Monk slope distribution, just deciding it's flattened slightly by the wake if it's set above 0. Here are some quick examples of how the wakes would look in our final renderings. As you can see in these pictures, the wakes themselves, while maybe not as intense as the ships themselves, they are very large and very visible. And that makes them very important in the detectability of a ship, which is something we wanted to incorporate in our software to take into account. So let's move into how we model plumes. MuSES can model exhaust plumes for added signature accuracy. As you can see in these pictures, oftentimes these plumes are much hotter or larger than the actual target themselves. So ignoring any plume themselves will underestimate the overall signature. To do this, MuSES imports volumetric CFD results from an external analysis. This calculates a plume radiance when creating rendered images of the target. This plume radiance is only calculated for ray tracing paths between the scene and the sensor, which pass through the area of the imported CFD results. We can also support the inclusion of CO2, H2O, and carbon soot as species within the plume. As you've seen, a lot of different information goes into making a target model, and adjusting a lot of it manually to create an image data set can be tedious. However, we do offer ways to automate some of that with another one of our TAI developed software, Cotherm. So inside of each model, we have the geometry of the target, optical surface descriptions, and terrain descriptions. These are all fed into MuSES along with weather data and sensor parameters to create a thermal model. And after that analysis, synthetic images of the scenes are generated, which can then be fed into an algorithm to give some deep learning output. To generate these types of data sets, we developed Cotherm. Cotherm is our co-simulation and process automation tool. It's often used for complex multi-physics simulations that require coupling multiple software packages together. But it can also be used to automate a repetitive process like MuSES thermal and infrared predictions over a wide range of variables. The Cotherm user interface is shown here. There's a process flow chart made up of a series of simple tasks that run to completion. So we're able to provide a GUI-based path for generating these large IR data sets of interest in an efficient manner. And we can quickly run through one example of how we generate these IR data sets. So here we can see an example thermal model that we could feed into our data set generation process. This is a type 054 frigate for which we have spent time generating a high fidelity geometry representation and accurately parted out geometry descriptions based on differing boundary conditions of the craft, included heat sources such as solar loading and engine heating. We can then analyze this thermal model and render it under numerous conditions. Here we analyze the target while it was off, idle, and exercising at numerous points throughout the day in an open ocean, as well as with a littoral environment background behind one of the images. And we created over 2,500 simulated long wave images for our desired sensor. And you can see a number of images here. The one on the left is when the model is off, so no engine heating, it would just be solar loading, or if it's at night, just any remaining heat from the day. And you see different wakes in the second and third image, and you can also see one with a physical littoral background behind the target itself in the last. So by combining MuSES and Cotherm, we're able to efficiently generate these large, accurate, and automatically labeled sets, which can be used for training and testing various AI ML tools, such as those for target recognition. And obviously we can do many more than just maritime, including humans, ground vehicles, aircrafts, UAVs. All right, so let's go back into just the maritime stuff and look at some more examples here. This just shows a few of the variations, different types of ships, as you can see, anything from a simple raft to multiple destroyers or frigates together, using different types of sea states or the unstructured sea versus the structured sea, as well as having a littoral background. Like the bottom three on the right show three of the same model, but in different wavelengths, showing that different bands are also possible, as well as some more close-up images with some good lunar glint there on the left side in the near IR. So throughout this webinar, we have seen that thermal analytics can model high-value maritime targets across the IR spectrum. We use these models to generate large and varied image data sets. These data sets are growing in popularity with the increasing demand of AI ML training material. And we have already been working with many different customers with their AI ML workflows to help speed up that training process. And with that, I can open up the floor to any questions.
Some questions here. Is it necessary to properly attribute heat sources under the waterline?
Yeah, so it depends on what type of heat source and where it's located. I can actually go back to a slide that shows more part separation. So parts like the engine, and especially in larger ships, are probably going to be underneath the waterline. And that's obviously very important because that heat translates up through the internal cabin and will be shown on the exterior surfaces above the waterline when you render images. But heat sources such as like propeller friction, obviously all renderings are going to be taken. You're just going to see the water rather than any of the actual underwater heated sources. And especially with our structured and unstructured sea, any heat given off by the ship will not convect into the sea. The structured sea created is its own temperature, which, you know, in real life, in a real ocean, it'd be pretty hard to actually change the water temperature to make any differences in renderings. So that's not super important. So I'd say the internal sources that will affect the above water geometry are definitely important, but things like propeller friction are not that important.
Okay, thank you. I tend to see simulated ships represented with much less IR intensity than what is seen in thermal images from thermal cameras. Could this be due to not modeling solar reflections?
Yeah, that could definitely be due to solar reflections. Like our software, as seen in like these images, take into account both the sun or lunar glint within an image, as well as any of the thermal aspects of the target itself. And we do use ModTrain to take into account all of that atmospheric changes as well. So I'd like to think that our images would be a little bit more accurate than what you've seen in the past.
Okay, thank you. Can you discuss how your wake is affected by choice and wet facets as defined by picking your waterline?
Yeah, I can actually go a little bit more into depth on the wake slide. So you can see these inputs in the top right here. So you can enter things like ship class, and I wanted to go a little bit more into depth on this. So the waterline length itself, a lot of these are based off of the ship itself. So the stern width here is set to 16,400, and that's in millimeters. And all of these things would be inputted based off of whatever ship you're using. So using that displacement and draft of the ship, as well as the location of the stern center, all of those would be inputs into this wake. And then it also takes into account the inputted water line from the one slide that I showed previously, right here. So all of that would go into account when actually creating a wake. I hope that answered your question.
All right, thank you. In littoral scenarios, does the wave period shorten as the waves approach land?
No, so the way the structured sea around the ship itself does tend to ignore any littoral geometry. We don't have a way to have the land itself affect the waves. But if you're taking images far away, that tends not to matter. And a lot of times you wouldn't want to generate a structured sea super large, as that would take a massive computation time if you had waves continuously between the ship and the littoral background. But
Okay.
yeah, I mean, that's something that we can look into as well.
Thank you. Can you give a sense of runtime?
Runtime. Oh, sorry, you're cutting a little bit. Can you repeat that?
Oh, sorry. Sense of runtime to render an image, i.e. 4K by 4K pixels with high fidelity ocean.
High fidelity ocean, I would assume you mean structured C by that, 4K by 4K. I can't give you an exact answer. But I've rendered stuff before, tends to take less than a minute. Obviously, if you have a complex, if you have all the atmospheric selected to take into account, it depends on how much of a structured C and a wake you need. I can look into that a little bit more and answer that better, but I would less than a minute for sure.
Okay, thank you. Does the model generate bow spray where appropriate?
Can you repeat that again? Sorry.
Does the model generate bow spray where appropriate?
Oh, no, it does not do that. At most, it does a little bit with the wake, but to get more complex spray like that, you would have to import a CFD calculation into our software, which is possible, but our software itself does not create that geometry.
Okay, thank you. For moving ships, does the ship move with the sea state?
No, the ship will stay steady. The sea state generally only affects the surrounding geometry.
Okay. Excellent. Well, thank you. If we did not get to your question, we will be following up with you directly following this webinar. That will complete the webinar. We appreciate everyone for attending. Thank you, Eli. You will all be receiving a follow-up email containing links to download the presentation slides and watch the recorded webinar session. Again, thank you everyone for attending. Thank you, Eli, and everyone. These are our upcoming webinars. If you're interested, we have them posted on our website. Feel free to register. And thanks again, everyone. Have a nice day.
Yeah, thank you for the opportunity. Thank you all for coming.